Okay, I guess because so today need to do implementation plus region policy.
Okay. Hello everyone, I am Hong Yige. Today I'm going to introduce an algorithm called trust region policy optimization. Many reinforcement learning algorithms can be built under the framework of generalized policy iteration, which includes two phases, policy evaluation and policy improvement. During policy evaluation, the value function of the policy is evaluated, and during policy improvement, a new policy is generated in term with respect to the current policy and the policy estimation. The problem with many reinforcement learning algorithms is that they do not give monotonically improved policy, which means the new policy generated in each iteration does not necessarily improve over the current policy. And this sometimes can cause some instability and makes the algorithm less effective. And trust region policy optimization is motivated by this problem, and it approximates a procedure with guaranteed monotonic policy improvement. And it is also defined to be effective for optimizing large nonlinear policies. This is the outline of my presentation. First is problem setup and notations. Then I will define some concepts and prove some theorems. Third is the prototype algorithm with guaranteed monotonic improvement, based on which the trust region policy optimization is developed. The fourth part is trust region policy optimization, including its formulation, experiment, and implementation. And finally, I will introduce a little bit about proximal policy optimization, which is simpler to implement than trust region policy optimization and achieve the similar effect. The MVP is defined in this way. The S is state space, A is action space, and P is the transition probability. R is the reward function. Rho 0 is the distribution of initial state, and gamma is discount factor. Also, a stochastic policy pi is defined as the probability for choosing each action on the every state. Also, we define value functions, state action value, and advantage in the following way. The state value is defined as the discounted total reward given the initial state under the current policy pi, and the state action value is the total reward following initial state and initial action on the current policy pi. And the advantage is the difference between the state action value and the state value. And the advantage kind of measures how an action improves over the action taken by current policy. And our goal is to maximize the total reward under this MDP. Oh, okay. Yeah. This action, this A does not exist. To define monotonic policy improvement, we first need a measure of policy performance, which is the long-run expected reward. It is the expected total reward under a policy pi, given the initial distribution S0 following rho 0. And we also define a state distribution called discounted visitation frequency. It is the probability of visiting state S over all time steps. In order to find improved rho, yes, just discounted sum of all the probabilities.
What's S1?
S1 S0 Si is the ith state generated in the trajectory. I mean, generate a trajectory using a policy pi, and the Si is the ith state in that trajectory.
So the pi of this. This is the I don't remember. So this is not stationary distribution then.
Not station distribution.
This is
It can be viewed as a point, kind of station distribution to gamma discounted MDP kind of.
Yes, I think it is when gamma approaches 1, this comes proportional to the stationary distribution.
No, I mean if you introduce one transition states to the original MDP, that means you have the probability to restart or something, and this will be the stationary distribution of the new MDP.
Yeah, maybe. I'm not sure. I think this term is just defined because it appears later in the maybe in the computation of eta pi or some other quantities.
This is the first time I see this. Is this the? Okay, I guess how to sample it, right? The in reality, the computation you need to do, but how do you estimate? What will be the estimate of something that let's worry about later. So this non-run expected work you say?
Yeah, I think it is maybe called this.
Are you copied on the terminology in the paper or no?
I think copied in the paper.
Okay. It's disturbing term.
When generating a new policy, we need to measure how much it improves by using the difference between the two eta. Eta pi theta is the performance of a new policy pi theta, and the eta pi is the performance of the current policy pi. And the lemma shows that this difference can be written as an expectation, which is related to the advantage on the pi, and the expectation is taken over the trajectories, all the trajectory generated by a new policy pi theta, and this difference can be also be rewritten in terms of the state distribution rho pi theta, and it equals to this, which is by first taking the weighted average of advantage function using the pi theta, and then taking weighted average using the state distribution rho pi theta.
Before I think all the motivation are on this slide. Something more can be said or should be said. right?
Okay.
So you want to do the policy improvement, right?
Yeah.
So currently the pi policy part. You want to find pi tilde be better than pi.
Yeah. Yes.
Right? Okay. So which means you want to find something on the right side of 6. You want something again here is what you want to
Maximize.
minimization or maximization.
Maximization.
Maximization. You want to maximize right hand side of 6. Right?
Yeah.
Okay. Now everything 6 the computation is hopeless, right? You need to do a lot of sampling right now. Okay. So the pi is something. Okay, maybe I let you talk. Okay, you need to talk about it.
Oh, okay.
Yes.
Okay. We need to optimize the right hand side so that it becomes positive. When it becomes positive, the policy will improve. And however, from equation 10, we see that this term involves the state distribution rho pi tilde, and the rho pi tilde is the dependency on rho pi tilde on pi tilde is very complicated, and computing this requires the whole knowledge of the system transition probabilities, and this one cannot be directly optimized.
You say rho pi tilde is a relatively computer.
Yes.
Okay.
Maybe for a specific pi it can be computed, but here pi tilde is a variable. So if we want to, for example, taking derivative with respect to pi tilde or some optimization steps, this will become infeasible. Therefore, we define a new function called policy advantage L pi pi tilde, defined as approximation to the eta pi tilde, a local approximation to eta pi tilde at the current policy pi. It is the only difference with the eta pi tilde is that it replaced the state distribution rho pi tilde with the state distribution rho pi. State distribution under the current policy. So the dependency, only term that dependent on the variable pi tilde is this one, and this function becomes much easier to optimize.
So again, that's the only change here from previous formulation. The rho pi tilde. Let's say cost distribution. I don't have a better term. So distribution for pi tilde you're looking for, right? So that's a variable.
Yeah.
That's difficult to deal with that.
Yeah.
So just as heuristic, replace that distribution by fixed point distribution.
Yeah.
Which is this one is and the current policy you probably already know or you have a lot of information. Right?
Yes. And this heuristic can be somehow justified that because it is first order approximation to the true quantity, which means that when pi tilde equals pi, they are equal, and when the gradient of this one is equal to this one when pi tilde equals pi. However, when only using approximation is not enough. By optimizing the L pi pi tilde, we does not necessarily give and improve the eta pi tilde. We should instead use a lower bound of eta pi tilde, and the lower bound is defined in this theorem.
Before you go So I actually don't understand first part. Approximate. Approximate
a hat.
What's the advantage function?
Approximation of advantage function.
Advantage function because we cannot compute the advantage function exactly.
Yes.
That's an approximation.
Yeah.
Right. Then so optimizing optimizing that L pi character, that will not necessarily improve. Is that because of it's because of the main function cannot be computed exactly, therefore this cannot improve or something else?
Yeah, when it can be computed exactly, it actually still improves because if you maximize, when it can be computed exactly, optimizing this can still improve. But when it is a little bit inaccurate, you cannot give any guarantee whether this new policy will improve the eta pi theta.
You mean that's equal to 0? Is this if pi theta replaced by pi there, that's will be 0. That the second term is 16.
Yes.
Here, right?
Yes.
So that's what you mean by that way. At least not worse off, right?
Yeah, not worse off.
Is that clear here? Replaced by the pi theta by pi, that's 0. So that's okay. So since it works because of approximation.
Yeah.
It cannot be computed exactly.
Okay, this is the theorem. It bounds the eta pi theta with L pi pi theta, and a constant term multiplies the maximal KL divergence between the between the KL divergence of current policy and the new policy pi theta. The maximal KL divergence is maximizing over different states. For each state, the policy defines a distribution, and we compute the KL divergence between them, and then we maximize them over states. This is the definition of maximal KL divergence, and this defines a lower bound. Okay, the proof of the theorem uses the idea of coupling. Alpha coupling is defined as if two distributions.
I suggest you skip this for the moment.
Okay.
This band accepts this band, and motivating why we use it, why this band is useful, and how to use it. Coming back to this book. Okay.
Okay.
Suggest that, right? I mean, your motivation is very clear. I think that A is the approximation, then the optimization problem may not give you improvement, right? That's very challenging to face. Okay, so presumably this band can help to resolve this issue.
Okay.
Right. So just don't stray away from the main method. Okay. They said they cannot hear me. They cannot hear my comment. So what should we do? Should I use this microphone?
No, but you have.
Echo.
Yeah. Maybe you should.
You can. When I talk, you can turn them off.
Okay. Yes. Yes.
Yeah. So maybe I should have let them. You can mute me. Right. So, is this an echo? No, then in that case, don't turn. Then I think I use this part.
Yeah.
So how many people are there? 5 or 50 people.
Yeah, 6.
Who is that man there?
It's this phone.
What? Can you turn off? Yeah. That's you, Mark. Is that right? No.
The first one is this one. The second one is this phone.
This phone?
Yeah.
Okay. Okay. Good. All right. Good. So I suggest that this low bound lemma to be proved later, or CM, and stay away from. So because that a point was made that when the advanced function is computed approximately, then solving that optimization problem will not necessarily improve the policy. So you need some more robust scheme to do that, so that it's actually the improvement. And so I presume that's the reason to get the you have different optimization problem, right? Go ahead.
Okay. We have already got that lower bound, and then to get a new policy, we just maximize over that, find the policy that maximize that lower bound. And this 43 shows that this policy actually improves the true objective eta pi. Because eta pi star is larger than the lower bound pi star, as it proved.
That's by definition. First one is by definition, right?
Yeah, by the theorem, by the bound.
First one
yeah,
is by the bound.
By the bound and the definition.
The bound is pi eta star. Go back to the bound.
Oh, okay.
Right. And pi star bigger than everything by star, right?
Yeah.
And that star is equal to maximization of the right the left hand side, right?
Yeah.
Okay. Good.
The eta pi star is larger than the lower bound pi star, and the lower bound pi star is the maximization of the lower bound, which is larger than the lower bound when the pi tilde equals pi. And when pi tilde equals pi, the KL divergence vanishes. And by definition of L pi tilde, the L pi equals the eta pi. So this line proves that the policy that maximizes the lower bound also improves the true objective. And this is actually a kind of minorization maximization algorithm.
But this, I mean, if you can argue this also, you may have suffered, right? Previously, you said you cannot solve this exactly, this one, because the advantage function need to be approximate. But this only assumes that solving this optimization problem, you can solve exactly or something, right? You do not suffer that problem. Let's see, or maybe this one is more tolerable to the approximation.
Actually, this one is more tolerable than approximation using only the L pi tilde. In this paper, it does not consider a case when the estimation is inaccurate. In a previous paper called a conservative policy iteration, it proves that when the estimation, when the lower bound is larger than 0 for some degree, and when the approximation is small enough, this will give an improvement. On the other hand, if we only use this one, maybe a little inaccuracy in the estimation will give a bad new policy.
You said previously it's not this paper, other paper talk about it.
Yeah. Yes.
Right. Other people talk about. So this is something, right? The first problem you talk, unfortunately they cannot hear me. That's okay. But that's when maybe when disadvantage of being away, right? So so the first problem need approximations, and this new version problem more tolerable to the error in the approximation, right? That's basically the other papers already established this. Okay, that's main motivation. Okay, good. That's very clear. Yeah.
Next, this is the pseudocode for this for prototype algorithm directly follows from the theorem. In each iteration, it computes the advantage values a pi and use the a pi to compute the surrogate objective, the lower bound. Then it maximizes over lower bound to get a new policy. This new policy is guaranteed to improve monotonically. and we repeat the iteration until the algorithm converges. This is the prototype algorithm, and the transfer region policy optimization is an approximation to the prototype algorithms. It made several changes. The first change is changed the penalty, the KL divergence penalty, to a hard constraint on KL divergence. The motivation to do this.
So now you change the notation, right? So the policy pi is parameterized by theta, right? Okay, so everything theta is the pi, right? Theta tilde is pi tilde. Very good. Okay, good, very clear. So you change the problem. 45 is right. It looks like 45 is that it's equivalent, or it's just different problem. 45 is equivalent to 46 and 47, right? Or in general, it's not same.
Not the same. Not same. Just heuristically, they are similar. Almost the same problem.
Really? This is something that we have a lot of optimizer here. So can I say something here? Is the solution to by properly choosing delta? Are they being made to be equivalent? Do you have comments?
I think they are not not necessarily equivalent. Maybe this one is a hard constraint on KL divergence, and this one is a kind of a soft constraint on KL divergence, which means when this one is very large, maybe it will the actual KL divergence may not be bounded.
Well, suppose bounded. Okay, let's say something. I assume the both have 46. Suppose theta star is the optimal solution, 45. Right? Suppose theta star is the optimal solution here. Right? So star is the optimal solution. Then I will use choose delta to be this value. You know, it's realistically, of course, practically, you don't know what delta is, right? You don't know what's that to search. It's the case. I'm sure something more can be said. Can I say the exist delta that these two problem equivalent? No.
No, I don't think so.
Okay. Good. Yes. They should be equivalent. Right? Maybe there's a yeah, multiply. Yeah.
Okay. So CYC is the Lagrange multiplier. They are equivalent. Oh, okay. The second change is the changing from maximal KL divergence to average KL divergence. This is because the maximal KL divergence is not tractable when in practice, because it's maximizing over all the states. Instead, we should use average KL divergence to approximate the maximal KL divergence. The average KL divergence is defined in this way, which is averaging over the state distribution rho pi. Oh, there's a typo here. In the expectation, there should be a DKL.
Do people understand something here? Why this is the divergence on the two distributions? Let's see if the audience already got lost. Yeah. Because if it's lost, there's no need to.
So the equation 48 has something missing inside the expectation, right?
Yeah, there should be a notation for KL divergence.
So can you remind us again what is pi, like DL max and the pi, all of this stuff, notations? It's a bit messy here.
Oh, the DKR max is first compute for each state.
Do you have more definition better style than this?
No.
No.
What's the mathematical definition of KL divergence, KL max?
Well,
Between which two distributions? How are these distributions defined?
Okay, so let me something. This is something I'm afraid that if audience got lost, they think everything got lost. So look at 48. Okay, 48 is a dot, meaning it's a distribution on the actions. Okay, distribution on action. Pi, 48 has pi there, right? For has a pi is a distribution. For every fixed state S, you need to make a decision. The decision is randomized. You have this choice, that choice, and it's a distribution. Distribution tells you how to make decisions, right? So pi is a distribution. Pi theta tilde is another distribution. So these two distributions, you can measure the distance. KL distance is the one to measure that.
I see.
All right, is that clear?
Yeah,
Now,
that's clear.
this has many states, okay? So the max is the amount is among all the states, choose the maximum distance, KL distance, among all the states. That's max, okay? The max. Clear? That's definition. All right, now the other one, he's trying to define the rho pi one is a so-called averaging of the KL distances depending on state. Remember, it's averaging over all the states, okay? And the weight coefficient using state distribution for that state. And the reason to do this is later, once you use state distribution, you can use a sampling, much easier to deal with that, right? The average. Is that clear here?
Yes. Yes.
Okay.
So theta, theta is a parameter?
Yeah, it's a parameter for the policy.
Oh, okay.
So that's 49. 49 is all for notation, right? You see, 49 is all for terrible notation, right?
Yeah.
So
It's not
because
distribution. Like this looks like a theta and theta tilde are distributions, right?
right. Theta tilde is just numbers. So
Yeah.
right, doesn't make sense. So it should be pi theta theta tilde.
Yeah.
Okay. So after these two changes, the first change from KL penalty to a hard constraint on divergence, then change from the maximal KL divergence to average KL divergence. The trust-ridging policy optimization is formulated as the 50 and 51. It maximizes the L pi tilde and subject to a constraint on the average KL divergence. Okay. This is the numerical experiments of the paper trust-ridging policy optimization. The y-axis is the average reward in each policy evaluation, and the x-axis is the number of iterations. The green curve and the blue curve are trust-ridging policy optimization, and other curves are other algorithms. And it can be seen that the trust-ridging policy optimization has outperformed other algorithms, and it kind of improve monotonically.
Did they talk about how to get that delta parameter?
Delta parameter. You mean
In 51.
51? Later talk about.
Okay, so this numerical experiment, they just by trial by error, that fix some delta to look at find policies.
Yeah, this may be some hyperparameter, just a fixed hyperparameter.
Okay, all right.
And this is the performance of trust-ridging policy optimization on a discrete task, a tally game. The columns are the different games, and each row is a different algorithm. The first row is a random algorithm. Second row is a human. The third row, deep Q learning. The fourth row is a model-based algorithm related to Monte Carlo tree search. And the last two rows are trust-ridging policy optimization with different ways of doing of estimating the objective, and
Different what?
different ways of doing policy evaluation.
All right. I think the more precise term is more different ways to estimate the advantage function.
Yes.
Right? Which you're going to talk about.
Yes.
Right? Okay. So different ways to estimate advantage functions, and which you're going to talk about. Okay.
Note that in this experiment, the trust region policy optimizing algorithm used the same set of parameters and architectures. Although its performance is not as well, in some tasks it's not as well as other algorithms. It is not too bad.
What? Say it again. Okay. So you claim that these two new algorithms are not too bad.
Yeah, not too bad.
The score higher the better, right?
Yeah, the higher the better, and they are not too bad. For example, on this the fourth column, it is almost the best, and on the third row, it has outperformed human and the deep Q learning.
Good. So can you comment on this your bullet point? I don't think every audience appreciate that yet.
Oh.
What's on your bullet point?
This means on this different task, the trust region policy optimization used the same set of parameters. It did not tune hyperparameters, and so although it's not very good, it shows that this algorithm is kind of general and does not require much tune of hyperparameter.
So first is what? First is so other algorithms, each game they specially tuned for that one, try to do best, right there. And this one, their algorithm is just one set of hyperparameters, do them all, right? So it's not tailored for a particular game. It's generic one. Whereas other numbers, other algorithms for each game here, they use the best one, right? Just specially trained for that one, for that game, right? So that's it. Am I right? Am I understanding correct?
Yeah.
Or is it saying that the parameters are not tuned from iteration to iteration? Delta can be adjusted per iteration.
I mean, the parameter, hyperparameter, not tuned. I mean, for example, the
Gamma.
the delta in 51 is not tuned, and maybe
it's used throughout all the iterations.
Yeah. It is still being trained, and through all iterations, the zetas are updated.
Yeah, but delta is fixed throughout all iterations.
Theta depending on game, particular type of game.
Yeah. Yes.
Right.
But that's tuned, right, per game. No.
Yeah. Theta is trained for different.
No, delta is tuned. I mean, chosen optimally or try and error for each game.
Delta is chosen by trial and error
per each game, right? And chosen optimally in a way, or greedily.
Yeah. Delta chosen by hand for different tasks.
Yeah. So that's what different from what Professor Dai just said, right?
Well. Yeah, I think for algorithm, the parameters, including some parameter that can be trained for each task, and some parameter that is tuned by hand, by trial and error, and what is fixed for in this experiment, what is fixed for different tasks is those parameters that is required to be tuned by hand.
By hand, what? Complete sentence. So, okay, Professor Lowe is asking, is the delta same for these problems, or they are separate? Delta 1, delta 2, delta 3, delta 4, or the same delta?
Delta is the same for all the tasks.
Oh.
And
No, you changed the story now. Is the same for all the games?
Yeah, yes, all the games.
so the rider and the invaders, they use the same delta for this new algorithm. Am I right?
Yes.
And other like deep learning, they use different hyperparameters.
Yes.
For the rider using one hyperparameter and invader using another hyperparameter.
Yes.
Okay. Did you understand Professor Lowe's question? He's exactly asking you to clarify this thing. You didn't understand his question?
Yeah.
So just a comment on policy, trust region optimization algorithm. Delta is typically changed from iteration to iteration. There's a deterministic rule to adjust delta from optimization perspective. But so now you're saying not only is this not changed per iteration on an iteration basis, it's not even changed across different optimization problems. That's kind of a scary statement to me.
Oh.
Yes, because the paper wants to show that this algorithm is not sensitive to the hyperparameters, so they do this kind of ablation experiments with the same delta in different tasks.
I think he should not use
So in trust region optimization, you typically have a surrogate model for the current cost function.
No, he's not
and then this delta is adjusted dynamically on the go.
Right.
I think in this algorithm, delta on a single task during training, the delta is not adjusted.
So it's not really truly trust region optimization, right?
Yeah, it's not truly trust region.
We are not hearing the conversation. Ask him to turn off his. Can you turn off your speaker?
Cool.
Yes. So why is the seminar stopped?
Go ahead, talk.
Actually, there is one version of adaptive on the delta. I think the Ego will introduce it later.
Okay. So the delta in this algorithm is fixed before. It is a hyperparameter usually the hyperparameter is changed from each task for each task. And however, in this experiment, for different games, the trust region policy optimization used the same delta and other hyperparameters. So this shows that this algorithm is a very generalized very well. And this one is the training curve of the trust region policy optimization. This is the performance of trust region policy optimization on the games. Here we use cost instead of reward, which means the lower the better. And the x-axis is the number of policy iterations. And well, in this picture, the two curves contains two ways of doing trust region policy optimization, as will be talked about later. And it just shows that these two ways, you cannot tell which is better. Sometimes one is better, sometimes the other is better, depending on specific tasks.
I missed something. So a vine and then single path. So can you elaborate on that? I think I stepped out a little bit.
I'm just going to talk about the vine and the single pass. And there are two ways.
You haven't talked about. Okay, sure. So this is so still you haven't talked about these two issues, right? Okay.
Go ahead.
Single path is basically one trajectory.
Right. He's going to talk about that.
Wow, a lot of noise. Okay.
You say you're going to talk about that.
Okay. So before we have formulated an optimization problem with objectives L pi pi theta, and to compute this objective, we need to first estimate the advantage or Q factor. And equation 50 and 53 shows how to compute the objective using the advantage or Q factor. In both ways, we need to compute the quantity that we need to estimate are the advantage and the Q factors, and the others are for example, pi theta theta is already available. And the first way of estimating the Q factor is called single pass. Although it is called single pass, it actually samples several paths. It samples T trajectories with each initial state sampled from the initial distribution rho 0. And from the initial state, we generate a trajectory according to the current policy pi theta. And on each trajectory, we estimate the objective function L pi pi theta using the equation 54. The left-hand side of 54 is approximately equals the right-hand side of 54 as the n and the t approaches infinity, which means as the number of trajectories and the length of trajectories approaches infinity. And the approximation of the Q factor in equation 54 is computed as in 55, which means for each state action pair, a pair on the trajectory, we compute its approximately compute its Q factor by finding out all such state action pair on the trajectories and compute their compute the compute the total reward happening after the stage action pair. In this way, we get the objective function L pi pi tilde.
What do you say is multiple episode? Is it one episode or multiple episode?
Multiple trajectories.
Multiple trajectories. So how do you use that one? So here you use what's the tau there?
The tau means the trajectory, and the AT and ST are the action and state on that trajectory.
Yeah, but your notation doesn't have tau in there at all.
So AT has a tau there,
Yeah,
ST has a tau there, right? Okay.
And then you have pi over pi. What does that? Can you explain that? Previously, you had this row there.
This is off policy correction. Because your trajectory sample from pi theta and you want to estimate the pi theta tilde, so there is some important sampling things like that.
Can you explain in more detail?
In this sum t from 0 to n, the probability for each state st, the probability of at to appear is pi theta at st, because the trajectory is sampled according to the pi theta. So there is so the pi theta is in the denominator, and when taking expectation, the denominator will cancel out, and the numerator will leave, which becomes the something on the left.
Okay, so the rho pi theta factor is taken care of by this 1 over t average, right?
Anyone can better explain that? Why is it divided by pi?
So this 1 over t average takes care of this rho pi theta, this expectation, right?
Yes. Yeah, the state distribution is following the rho pi theta.
Okay.
The tau multiple one take care of this one.
Takes care of the rho pi theta thing, right?
Multiple samples take care of rho pi theta. Okay, and this is divided by this is divided by pi, right? Divided by pi that's it. And what he's doing that for, forget about this point here. Now he's evaluated the second part. This part here, this part he using one sample to approximate the summation, right? One sample is using the expected value, right? Expected value of that, and expected value according to the expected becomes a pi. Okay, so everything averaging over. So this one is the expected value of in terms of pi. Okay, in terms of pi, the Markov chain, at evaluated at the state is s. Okay, one sample. So you just this is the let's see, no, not one sample. This is using the Markov chain among the n steps to approximate this summation pi times that, right? So that's pretty bad.
Basically, we can go back to lemma 1 is just sampling on the lemma 1.
Is that lemma 1?
Yes, it is lemma 1.
And the 7 and 10 is equivalent.
10. So
10 is equivalent to 6, and in 6 we replace A with Q, and it becomes it just becomes that estimation.
right. So the 10 is first of all, rho pi tilde is already sampled according to pi, right?
Yeah.
So this is expected value. Okay, this is space value in terms of station building for pi, right? That's sample of that. This second one here, there's no space value written down here. There's something missing. So it should be divided by pi, multiplied by pi. Then it's becoming space value plus pi, right? All right. I wish I have thought to write it down here. So it's really what he has is space value of pi. Space value of pi. So that's a summation of pi s pi divided by s pi delta a s these things, right? This summation, this one here, that's going to be space value. Space value of this is the stationary version, right? This has no t. Is this has t there? Does this have t there?
No, it does not have t in China. Because t is all contained in the rho pi theta.
Oh, okay, I see. Okay. So that's the value of pi, the value of pi. Delta divided by pi. And so this is the value can be a positive value using Markov chain approximation. Good. Okay.
This is about single pass evaluation. The second way is called.
I don't think they probably appreciate that one. The 55 is really key. Single pass everything. I wish you have a picture, right? Okay. So you have long trajectory there. One single x from S0 to the end, right? From S0 to the end. But everything here, you have STAT is the middle of the episode, right? Middle of that way. From here to the end, you can still observe part of the trajectory, right? So it's using from this to the end, this AT is the middle of that, until the end, whatever the cost collected, that's going to be this one. This will be very efficient. One sample pass can collect the cost of Q function value at everything middle point on the path. Right? This is very efficient. Instead for, oh, this is the middle of the class, I need to simulate this for 100 days or 200 days, right? Something. Here, once this was towards the end of the path, what's remaining is a very few data points to allow you to collect the total cost, right? So this one has more noise as towards the end.
Yeah, yes, the single pass evaluates the state Q value for state action pair on for all state action pair appear on the trajectories. The next the meaning of summation 54. You mean this one? Oh, this means
how many x?
Summing.
Capital T.
Yeah, summing over
from 1 to capital T.
Over trajectory, and this action state are from the trajectory. Okay, the other way is called vine. Instead of estimated state action pair for all the state action appear on the trajectory, it don't only estimate them for a rollout set that generated according to initial distribution and current policy pi theta. The rollout set generated in this way, its distribution is kind of the stationary distribution, and for each state in the rollout set, we estimate the QSA for its action. When action space is small.
So, slowly, okay. The rollout set, I don't think. Ask everybody, do they understand? rollout set. I trust that most of them don't understand, but they don't answer. They don't ask questions. They are very silent.
I think it's just using current pi theta tilde to generate the trajectory, right?
Yeah, yes. Yes, we use the current policy pi theta to generate the rollout set, so that the rollout set is the distribution of rollout set is similar to the stationary distribution.
So let me now ask a question, okay? Since nobody says that. So you have a row 0 to generate initial set of states, right?
Yeah.
So there's S01, S02, S0.
Yeah, I think that's the difference. So instead of starting from S0 all the time, you're going to generate multiple initial states according to row 0. That becomes a vine,
That's
right?
the thing, right? That's multiple initial states, right?
Right.
Okay. Then using for each fixed initial state, you're using pi, the policy, to run simulation. Am I right?
Yeah.
For certain length.
Yeah.
Whatever you observe during this episode, every state is recorded into the D. Is that right or not?
Yeah, yes.
Okay, you can explain this. What's rollout set? Instead of spell out a rollout term which nobody knows what the rollout set is, you can specify that, right? Okay, good.
So we generate a rollout set by first sample initial state from the distribution, and then for each new state we use the policy to generate a trajectory, and then we record all the things appear on all the trajectories into a set D called rollout set. And as shown in the previous slide, the set generated in this way approximately follows the stationary distribution on the policy pi. And using rollout set, we use the rollout set as the start point to perform many rollouts and estimate the Q factor for the SA in the rollout set.
Is the rollout set is really needed to use pi state on there? Can you just row 0 generate rollout set?
No, because we need to have the rollout set distribution same as the stationary distribution or under this pi theta. So we have to use the pi theta because to compute the L theta there is a term, this term rho pi theta here. So the distribution of D rollout set should be considered.
Right. So, okay. So the issue is that okay.
So the L theta is in equation 56. The L theta is can be estimated in this way. We first
you still have pi theta tilde, right? You still have to do something similar similar to before.
Yeah. Theta is a parameter, and sometimes use the theta in place of the pi theta.
You have to do this important sampling again, right?
Yeah, in 56 there is no important sampling.
Yeah, but this is not implementable, 56, because you have pi theta tilde, which you don't have.
Well,
These states, this rollout set is generated by pi theta.
yeah, it is. 56 is computable. We actually estimate the whole function with the variable pi theta tilde, and the pi theta tilde is stored as parameter.
Or parameters. Okay.
For example, neural network, and we in practice we first do evaluation and store all the Q values, and when we need to use the value of L theta, we just fix our theta tilde and compute the compute the equation 56 to get the L theta theta theta.
I see.
So just a second. Okay, so let me sharpen my understanding. This entire thing, so-called row offset, is to deal with this averaging. Nothing else. Am I right or not?
To take care of the rho pi theta thing, right?
Take care of the rho pi theta, right?
Yeah.
Okay, so the rho pi theta, yeah, rho pi theta is not distribution, right? It's the particular way to define it, right? The particularly defined, you need, this is related to my earlier question, how do you do sampling for, how do you do the a computational scheme to how to compute rho pi, right? And this scheme is strange. Right? I found this thing is strange. Right? So you sample this according to rho. Is this rho pi?
Rho zero distribution of initial state, not the stationary.
What's a rho pi?
Rho pi is the, or it is the discounted state. It is not a stationary.
So rho zero is a stationary distribution?
Rho zero is the initial.
Rho zero is initial distribution. Oh, okay. Okay, okay, yeah. Rho pi, rho pi is not, yeah, I said it's almost like station distribution. So it's not, yeah, so rho zero, okay, now it makes sense, yeah. Okay. I think that's needed a separate argument, separate proof of something, this sampling is related, some unbiased estimate for rho pi, right?
And the 57 is a kind of important sampling version of 56. Instead of estimate for all the action A in action state space, it samples some of the actions, and kind of important sampling version.
I suggest you have limited time, so just skip this part. Now coming back to the other important part.
Okay. This picture illustrates the difference between the single pass and the vine. The single pass generate trajectories and estimate the state action value for every pair on the trajectory. And vines start from each state, generate a trajectory, and use the trajectory to form a rollout set, and then estimate the state action value for this state on the rollout set.
How do you find an estimate state value function at the rollout set, a point in rollout set? How do you do that?
In this case, we do for each trajectory of rollouts, we sum up, do the discounted sum of the reward as the estimate of a state action pair.
So for each, go back. So how do you estimate this one?
We start from the state S and action A. We use the pi. We use the current policy pi theta to generate a trajectory, and then we sum up the reward obtained on the trajectory.
Single trajectory.
Yeah, yeah. Maybe multiple is also okay. Multiple or single trajectory.
So for each in 56, for each state action pair, state is limited action. It's not a limit all the states, right? For this already sampled state, the rollout set, right?
Yeah.
You need to estimate this, and for this each such state, you need to run a simulation.
Yeah.
Maybe quite long, right?
Yeah.
To estimate that.
This one is just about how to do that optimization problem, and it's can be found in the paper's appendix. Just skip this part. There's another algorithm that achieves similar effect as a trust region policy optimization, while being simpler to implement. It is called proximal policy optimization. It proposes a clipped objective, as in equation 63. In this equation, the E hat means the kind of sample is empirical expectation sampled according to the current policy, and inside the expectation there is a minimum. The first term in the minimum is just the same as the objective in the trust region policy optimization. The RT is defined in here, as the quotient between the new policy and the current policy.
So this doesn't involve KL divergence, is that right or no?
It does not involve KL divergence.
It does not cover that. So it's the same as something. So I'm already confusing. Okay, I'm confused now. Trust region 1 has a KL divergence or no KL divergence?
Has KL divergence.
Okay, so you're already mixing up things, right? You're confusing us, right? So this one you said similar to the trust region 1. There's no KL divergence in 63, right? Okay, so it's better for you to compare 63, which is with the earlier ones. Is something that is there any special case like epsilon equal to 0? Does that or something? This does not reduce to anything. The previous is there like a minimize L epsilon L pi?
Yeah, the algorithm is by minimizing the L clip. Or by maximizing the L clip, and when the epsilon in the clip term approaches infinity, the objective degrades to the objective in trust region policy optimization.
What's something?
When the epsilon approaches infinity, the second term in the minimum and the first term in the minimum are the same. And this one is the RTAT, which is just the objective in the trust region policy optimization. It's just this one.
You keep coming back trust region. Trust region has KL divergence. Right? You already told me that.
Yeah.
Why you keep saying these things that are confusing? There's no KL divergence, right?
Yeah, there's no KL divergence. It does not use the KL divergence as a constraint. It only optimizes the objective.
So right, this thing is everything that. Let's go back to the original problem. That slide to lemma 1. Right. When we do something, we first need to be big picture and not lost, right? So it's here. So this is what's the heuristic? Go back to the next slide. Yeah, this one here. So 16. You want to optimize this one, right? Want to optimize this one, and the optimize the 16 involving computation of A, which is difficult, which we often use the sampling method to estimate that, right? So which means only approximate evaluate that A. And you said previous paper already say that that is problem. Optimization of right-hand 16 may not be actually improving policy pi, right? Because the sampling error from evaluating this A, right? Therefore, KL divergence error, the low bound, that one, it's being introduced to try to overcome that difficulty, right? Because this A is a problem. A is an advanced function. You haven't talked about what's the impact. A is positive, negative, right? You want A is all positive, right? Which is very nice. But unfortunately, for some state A is positive, some state or some action A is positive, and sometimes the negative, right? These things. So the error you know, particular from positive to negative, that's where it change a lot, right? These things, okay? So your computation should be positive, your computer number is negative, right? That's where it be bad. Am I right? Okay, so the KL divergence is a more robust way claimed to be, okay? There is one way. Now, what you're talking about, clipping method, is an alternative way to deal with that challenge. Am I right? So not trust region, okay? No trust region anymore, right? Is that right? So don't say similar to trust region or something. It's different, right? It's a different strategy, different algorithm, right? To deal with the challenges. Am I right?
Yes.
Okay, so basically take advantage of sign of A is positive or negative. Am I right or what? So that let you talk, okay? So I just want to be oriented.
Yeah, trust region policy optimization is in practice by try to guarantee the monetary policy improvement by prevent the new policy from being too away from the current policy. And therefore, it uses a constraint on KL divergence. And the proximal policy optimization is an alternative way of preventing the new policy from deviate too much from current policy, so that it will probably make the policy improve. Somehow prevent the policy from getting bad due to the inaccurate estimate on the advantage or Q factor. He achieved this by taking a minimum of the two terms in objective. The first term in objective is just that one appeared in the L pi pi theta. The second term is a clipped term, which is clipped the quotient between the current policy and the quotient between new policy and the current policy. And this clip will when the quotient becomes larger, very large, and very different from the difference between the quotient of the new policy and current policy, and the one is larger than epsilon, the gradient of this objective will vanish, and this will prevent the new policy from getting too away from current policy.
So this 63 is another alternative way to maybe change new policy, change slowly. Don't change too much. Just
Yes. This picture shows that the clipped objective, the gradient vanishes when the RT, the quotient, when the new policy is very different from the current policy. The x-axis is the R, is the quotient, and the y-axis is the objective. When here we have A and multiplied RT, we want to optimize this term, and when the A is larger than 0, we want RT to be as large as possible. So without the clipped term, this will be straightly go up, and optimizing this objective will give a new policy that is very different from current policy. But
slow down. Okay. So when A is positive, meaning that's good. That's a good act. Good. When A is positive, then I likely want to maximize. I want to take that action.
Yes.
Right. When A is positive. But so the RT will be the pi tilde. It's likely the danger of the pi will be trying to go very, very high.
Yes.
It's very aggressive, right?
Yes.
But that A positive maybe is the false positive, right?
Yes.
Could be false positive. If the real A is truly positive, then you want this R to be as large as possible. Am I right?
Yeah.
Right? You're confident that's the best thing to do. But if A is a false positive, you have some chance to be false positive.
Yeah.
Is that right? So you not want to be aggressive too far.
Yeah. Yes. So this clip prevents when A is larger than 0. This clip prevents the new policy from getting too far away from current policy. Similarly, when A is smaller than 0, and we want to which means the action is not desirable, and we want to make the R small as possible. However, this smaller zero can be inaccurate and it can be false. So we prevent it from being too from changing this direction too much by doing the clip. This is the clipped objective, and the proximal policy optimization just in each iteration it's just doing several optimize this one by doing several, for example, gradient descent or something. The other alternate objective proposed in the paper of proximal policy optimization is the uses KL penalty. The KL penalty, just as stated in the original prototype algorithm, uses the KL penalty. However, the innovation is that the coefficient of the KL penalty is adaptive. This is to deal with the problem that this parameter is the coefficient of KL penalty. If we choose it as a fixed parameter, it is very hard to tune. So we makes the coefficient adaptive. Specifically, to adapt beta, need to first set a target distance, KL distance between the new policy and the current policy. And when the distance after each policy update, we have a new policy and an old policy. We compute the distance between these two policies. And if the distance is smaller than our target distance, we shrink the beta to make the penalty less strict, so that at the next policy improvement, the step will be slightly larger. And if the distance between the new policy and old policy is larger than the target distance, we make the beta larger so that the penalty is stricter, and in the next policy update, the distance between policies will be slightly smaller.
This is under what context? This is talking about the trust splitting algorithm, or this is talking about the
proximal.
clip?
Not clip and trust region. It is another way.
It's a third
way.
In today's talk, I think the third method.
Yeah, yes, the third method.
Third method is another optimization problem. Okay, third method. Okay. No need to go over detail here. Move on.
Okay. This is the pseudocode for the proximal policy optimization, which includes the previous two methods, a clip objective and KL penalty, and they can both use this pseudocode, which in each iteration it estimates the advantage and it forms the objective. It can be either the KL penalty objective or the clipped objective. Then during policy improvement, it optimized of the objective to get a new policy.
So here, the proximal policy optimization, you're really talking about three algorithms here, right?
Yes.
There's three algorithms here. So all can be okay. Why is it called proximal?
Because proximal means close, and it just makes the new policy close to the older policy. I think that's called proximal. That's all. Should I go back to the proof?
The low bound proof.
Yeah.
It's a 1030 already. Something. I suggest. Well, how many of you want to see the proof? Maybe go for a few elements. Yes.
Okay.
Something people can leave, can leave. Okay.
The proof uses a concept called alpha coupled. A tooth distribution called alpha coupled if there is a joint distribution with marginal P and Q, such that for any pair of random variables following the joint distribution, the probability that they are not equal is less than alpha, which means when alpha is smaller, the probability for these two distributions, these two distributions are closer. And there's a relationship between KL divergence and alpha coupled. When the KL divergence is smaller than alpha squared of the two distributions P and Q, if their KL divergence is smaller than alpha squared, these two distributions are alpha coupled. And if the two distributions are alpha coupled, for the same random variable, for same quantity, their expectation over these two distributions are kind of close to each other. And this is the idea of the proof. When the two policies are kind of this is a lemma that bounds quantity A bar S.
Okay. That's less interesting. That's just direct algebraic computation.
And this lemma is this difference. Left-hand side is the difference between two expectations, and the expectation term is appears in the computation of eta pi theta and the L pi theta.
So this is one using the alpha coupled.
Yes, it uses alpha coupled. It actually when the policies are alpha coupled, the states are also kind of coupled with probability 1 minus alpha times to the power of t, and these two differences can be bounded. And the proof of theorem is first to rewrite the eta pi in terms of the quantity A bar, and then their difference can be written as equation 38, where this term in the absolute value is just proving the last lemma using the coupling, and they are bounded. So the difference between the eta pi theta and L pi are also bounded, and this proves the bound.
Good. About here, I think that's good enough. Okay, the detail can be read on here.
Okay. That's all for the presentation.
So there's no comparison algorithm between these three versions of algorithm, correct? Versus proximal versus the trust region versus third one is the general adaptive KL.
There's a comparison on the paper on the discrete task, and the conclusion is that their performance are similar, and the clipped objective is kind of better, but clipped objective is slightly better.
The paper doesn't have numeric work.
Yeah, yes.
The clip is slightly better.
Yes, slightly better.
Okay. Good, very interesting paper. Good. Yeah, good job. Any other questions for them?
Do you have any questions?
Okay, good. Thank you.
Well, no questions, but one comment. And so your proof of the lemma, I think the intuitive things is that you just measure what's the difference for acting as pi theta, and okay, that's the definition. Right. So basically for one trajectory, and if it wants to measure what's the difference, so under the policy pi and under the policy pi theta, so basically so it separate it from two parts, right? So the first part is that when they are act in the same way, and from the point that they act differently, it starts to accumulate the difference, right?
Yes.
Okay.
Yeah, they start to accumulate difference as equation 25. When the t gets larger which means for later states, the error will become larger. But
Okay.
finally, it's still bounded.
Okay, it's very similar to the imitation learning proved like that. Maybe it's,
Imitation learning. I don't know what is.
Yes, there is some techniques like behavior cloning, some things like that. Okay, that's a separate issue. Okay.
Imitation learning.
Imitation learning.
Right.
Okay.
By the way, these three algorithms worth $10 billion. I mean, the OpenAI is based on these three algorithms. They're a bunch of product things.
So the OpenAI is mostly based on these three algorithms, right?
Yeah. The chief scientist is the first author of these two papers.
Okay.
Yeah.
So was $10 billion. Good. I'm sitting here, right? I mean, this trust region one, there's some lemma, there's something getting paper published, certainly is nice. I wonder, the other one, clip one, maybe less, less mathematical theorem, something intuition is clear. To me, it's more intuitive, right? The heuristic making more sense. So I wonder if there are more follow-up papers or follow-up lab work, numerical work, something. What's more evident? Is it really point to more to the clip algorithm is more promising or what? This is curious about that, right? Sometimes people publish papers because they have to add this thing, right? Add these things so that so they are mathematical proofs, right? So that the paper can be published, right? Sometimes different reasons. I don't know. I'm just asking questions. I'm not accusing them or anything, right? So you don't have any comments on that, right?
There's a study there's a paper named "Are Deep Policy Gradient Truly Policy Gradients?" And that paper studies the proximal policy optimization and the trust region and some other gradient policy gradient method. Their numerical results.
Okay. Mark, do you have anything to say? Nothing. I think it's interesting. This is definitely we should be familiar with this family algorithm, right? This one, and I think okay. So Yinglu's comment is 10 billion algorithms. Actually, it's good comment to remember, right? These first of all, making a lot of sense, right? This thing is a lot of things are implementable. Of course, there are many, even the second VIME algorithm, there are many different variations how to estimate, once you have rollout set, how to estimate this Q value. Another thing is everything in the discounted one, I still find this very artificial, discounted wide, discounted right, so here. Who knows if the average cost one is maybe more clean, it's a cleaner version, maybe something. And there may be cleaner version of the algorithm. So far, that rough thing is ugly. Okay, so let's stop here. Okay, good. So who's speaking next week?
So Liang Hao will speak next week.
Who's Liang?
Liang Hao is another student of Tom.
He just left. Yeah. Okay. I see. Okay.
Yeah, he will speak on the distributional RL, which is the very recent work of DeepMind.
Okay. But remind him how to organize slides. Okay. Again, today's slide organization is good generally. Okay, I like that outline, everything, right? You allow yourself to skip, not skip, right? The presentation. Do we agree the flow today is generally good? The flow, Yinglu?
Okay, okay, it's well.
Do you agree that today's flow is generally flow is good?
Yes, yes, it's clear.
The flow is good, and you want the audience first follow the general big picture, right? Then we choose to which part to elaborate, which part to skip, which is these things, right? That's the way to the presentation should be. Okay.
Yes. Actually, I helped him to polish the slides days ago.
Oh, good. Thank you. Thank you very much. Okay. Now you do the same thing for others. Okay. For the.
Maybe.
Okay. Please. All right. Let me. If they have questions, they can talk to me. Okay. Yeah. All right. Good. Have a good day. Are you new here? You just came. You are a student of?
No, I'm SC.
Okay. What's your name?